We have built the basis for the idea of mathematical induction. Oftentimes we want to prove something that has infinitely many statements, and it's impossible to prove infinitely many statements. So we've built this three-step process wherein which we have to essentially, to cause a chain reaction of stacked dominoes, if you will, to knock over that entire row of dominoes, we have to do a couple of things. One, we have to make sure every domino always knocks over the next domino. And that's a combination between these two steps here, the inductive hypothesis and the induction step. And then, of course, we have to initiate the sequence. We have to basically knock over that first domino. Remember, our analogy here of dominoes is really statements. They represent statements, and knocking them down means proving that that statement is in fact true. So for our statement here, where we wanted to show that a fast way to find the sum of the first n integers, remember that this notation means add up I starting at 1 going up to n. So this would be 1 plus 2 plus all the way up to when you would hit n. And by the way, this plus dot 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 plus is the way you write a summation to indicate that there's just a lot of terms in there. We don't know how many. Maybe not a lot. Maybe there's only 3, but in general, n could be a very large number. And that rather than to have n minus 1 addition signs, right? Because if you have n numbers, you'll have n minus 1 addition signs. That we want to show that that's the same thing. We'll get the same result if we take that largest value, that largest integer, multiply it by the integer plus 1 and divide by 2. We want to show that we get the same result. So the way we start off a proof like this is we prove the base case is true. Okay, in our case, n equals n naught. N is equal to 1 because that's the smallest value that n can be. Okay, so p of 1, we need to prove that the sum from I equals 1 and only going up to 1 of the integer I is equal to 1 times 1 plus 1 over 2. This base case step is often the easy one. It's very computational. So first of all, we have to establish, well, what's the left-hand side? So the left-hand side here, well, that's just going to be 1 because I starts at 1 and stops at 1, so there's no other terms to add to this. And then on the right-hand side, we have 1 times 2 divided by 2. Well, that is equal to 1. And so because these two are the same, we have proven that p of 1 is true. That's it. That's our initiate sequence. So we know that the first domino can be tipped over and it will fall. Next, we assume the argument is true for some arbitrary case, n equals k. So this step looks like this. P of k, or I should say assume p of k is true. What does that translate into? Well, this is the value that the summation goes up to, so we want to assume that the sum, I beginning at 1 and going up to k, of all of the i's. Okay, so this would go 1 plus 2 plus 3 plus 4 plus 5, all the way up to plus k. And, okay, what are we trying to say here? Well, our formula says that the sum from I equals 1 to n of I can be found by taking n times n plus 1 over 2. So this number here is the same as this number here, is the same as this number here. So if your sum went from 1 to k, then the shortcut computation would be to take k, multiply by k plus 1, and divide by 2. That's all we do in that step. We just assume that that is true. In other words, assume that there's some domino that can be knocked over. Okay, we already know that there is one that can be knocked over, and that's p of 1, but we're trying to be very general here. So we want to now show that when that domino tips over, that kth domino, it's regardless of what k is, it will always tip over that next one. So now we need to prove p of k plus 1. We need to prove that that is true. Well, what does that look like? Well, that would be the sum, I beginning at 1, and now n is going to go not up to k, but it's going to go up one more integer to k plus 1 of I. Okay, and we want to show that if we add up not just the first k integers, but we add up one more integer beyond that, that our formula will still work. Now remember, whatever this number is, that's this number here, that's this number here. We are going up to k plus 1, so that is our value of n. Okay. K plus 1 is our value of n in this case, multiplied by 1 more than that, so k plus 1 plus 1, so k plus 2 in other words. So think about this as it's the current integer times the current integer plus 1 divided by 2. So all we're doing here is we're just saying we need to prove that this formula, when we add up the k plus 1 integers, that's going to give us the same answer as what we have over here. I'm just going to simplify this a little bit. This is k plus 1 times k plus 2 over 2. Now, one thing you can do here is if you FOIL this out, it may just be easier. You'll see in a second. Let's FOIL this out and see what we get. If we FOILed this all out, we'd get k squared plus 2k plus 1k, which give us plus 3k, and then plus 2 over 2. It might be easier to show that summing the first k plus 1 integers is equal to k squared plus 3k plus 2 over 2, because otherwise we might end up with something that we have to factor, and it's easier to sometimes expand things than it is to factor. But both ways will work. Okay, so how are we going to prove this? Well, right now we don't know that this equation is true. So we have to start with one side and kind of operate on it. So let's start with the thing on the left and show that it gives us the thing on the right. And by the way, this is how most 99% of summation proofs will look. Well, the first thing that I'm going to do is I'm going to try to understand what this is saying. So this is saying I starts at 1, and then we increase I to 2, and then we increase I to 3, and then we go all the way up to, okay, now remember, the only difference between our sum in step 2 and our sum in step 3 is this includes one more integer. So what I'm going to always try to do is I'm always going to try to write my current summation as the summation in the inductive hypothesis. So I'm going to write 1 plus 2 plus 3 plus ... plus all the way up to k. Now, of course, that's this statement up here. But remember that this sum goes one more beyond k, so it will also include k plus 1. You don't have to have that in parentheses. I'm just trying to show that that's the extra term that we get here. Now, here's a little magic trick that we get to do. Well, this right here is the sum of the integers going from 1 all the way up to k. The reason we want to identify that is because that means we want to use what we've assumed in the last step to help us in the current step. So what does this equal? Well, I'd rather get rid of the summation, because keep in mind, to prove that the right side is true, there should be no summation sign anymore. So if I expand out the summation, if I write out all of those terms, or kind of indicate that there are all of those terms, incorporating the first k of them, well, what do I know? I know that this summation here that we have underscored is equal to k times k plus 1 over 2. Okay, that whole thing right there that's underlined is equal to k times k plus 1 over 2. Why? Well, because we assumed that for some arbitrary k that our formula works. And then, of course, I have this term here that needs to get carried down, plus k plus 1. That's pretty much 99% of the work right there. Okay, for the induction step, write out the left-hand side, expand it out, show the first k terms, one more term beyond that, take the first k terms, use the inductive hypothesis to substitute in what we have, and now our task is just to show that we end up either getting quantity k plus 1 times k plus 2 over 2, or we could just show that we get k squared plus 3k plus 2 over 2. Well, here's what we have to do a little bit of algebra. So to add these two things together, I know I want to get one fraction. So to get one fraction, I will divide by 2 and multiply by 2. So in other words, I'm just multiplying by 2 over 2 to get a common denominator. All right, so now up here I have k times k plus 1. Now that's over 2, but notice that now I have a common denominator between these two fractions, so I can add their numerators. Now, there's one of two things you could do here. If you're good at factoring, well, you could factor out a k plus 1 from both of these. And if you factor out a k plus 1 from both terms, I divide out a k plus 1 here, I get just a k. And if I factor out a k plus 1 from over here, I get just a 2. And you can already see that that numerator is exactly the factored form of what we expect to get. Now, maybe your factoring skills aren't hot, and that's okay too. You could also just distribute to get k squared plus k, and then distribute over here to get 2k plus 2 all over 2, and now you can combine like terms. 1k plus 2k is 3k plus 2 all over 2, and that's exactly what we were hoping to get. Now again, you could have saved a step here if you had factoring, and you could have also saved a step over here by not expanding it out, but I find that just expanding it out can be a little bit easier, especially if it's not as clear-cut to factor as it is in this particular scenario. Oftentimes it can be a little bit tricky to factor, so getting it into expanded form maybe takes a couple more algebraic steps, but it also doesn't require us to think as hard about the factoring piece. Okay, so what have we done here? Well, we have shown the base case is true, so we initiated the reaction. Then we showed that if one domino we know can be knocked over, the n equals k, this arbitrary domino, then we have established that it also knocks over the next domino. In other words, if this step is true, then this step is true also. If you can knock over one domino, it will always knock over the next one. That's the key piece here, because we knocked over the first domino, but we know that the first domino then knocks over the second domino, because that's the next one. The second domino knocks over the third domino, because that's its next one. And that sequence creates a chain reaction, and every single domino gets knocked over in this three-step process. So this is how induction works each and every time. The base case is usually the quickest one to do. It's going to be doing some arithmetic. Step 2 is a pretty quick step. That's an assume step. And then step 3, exercise some caution, but you're always going to try to expand out that left side, get the first k terms, use a substitution from step 2, and then do a little bit of operation on that to get what you are expecting. Remember, what we were saying here is this is what we expect to get. We expect to get that, or we can say that that's the same thing as this, which is the same thing as this. We expect to get that, and the question is, do we? And we just proved that we indeed do get what we expect, and therefore that means that that k plus 1 domino also knocks over. And so now we would just say, by mathematical induction, sum from I equals 1 to n of I equals n times n plus 1 over 2 is true for all integers n greater than or equal to 1. And that concludes our mathematical induction proof.